Hello everyone, welcome to this new FAULHABER webinar. To let other people join us, just a few words about FAULHABER. FAULHABER was founded in 1947, now is at its third generation. The headquarters is in Schönau, 20 kilometers south of Stuttgart, and we have 14 locations for research, development, and production in Europe and in North America. As a drive system solution provider, we can provide motors, encoders, gearhead, linear actuators, drive electronics, but not only this, we can modify the product and design everything tailored around your application. As you can see, we have 30% of our production is a standard off-the-shelf components, 30% is complete customized solution, so tailored around your application, and 40% is modified solution, so modification on the mechanical interface, cable, connectors, and so on in order to fit your requirements. Welcome to this webinar. My name is Mario Zecchin. I joined FAULHABER Group in 2007, first as a product manager for motion control. Now I'm currently in the digital sales system. I take care about the trainings and webinars and the e-learning system for our sales force. The maximum performance from your drive system is the title of this webinar. We want to give you information how to achieve the best results using the FAULHABER drive systems. You will see a lot of possible application selection. You can see a lot of information how to maximize the performance. For example, we start from knowing what is the main requirements of your application, and then we will talk about the drive system working points, because this is an important starting point, and we will see how to maximize the battery charge, long lifetime for the battery, how to operate in the maximum speed range, how to squeeze out maximum power from the motor, and how to reach the maximum torque, what is the condition where the drive system has to satisfy in order to withstand this extreme condition. Then we will see also how to reach long lifetime if you want to get the best from your investment. So let's start with a good starting point is know what you need. Everything depends on the characteristics of the application. Basically, we need information about the speed and about the application torque. This is the main requirements when selecting a drive system. Other requirements are necessary, for example, the size, the mass, environmental condition, what is the temperature, what is the range of temperature if you are working under a vacuum condition, for example, what is the axial and the radial loading if you have to apply some external belt system, for example, or an external screw. And the main constraint is the winding temperature. During operation, the motor will reach a stable temperature, or we have an excursion of temperature, and we have to take care that the winding temperature of the motor must be below a critical value. This is the most critical parameter to consider in the selection. If your application is a battery operated, then high efficiency drive system give a plus in your application, because the charge battery will last longer. You may choose a standard off-the-shelf components. Maybe when you select our drive system, you select the standard one, then you order, you start testing, and then you realize that maybe you need a little bit different motor, you need a connector, you need a different temperature range, or operating under vacuum. So we are here to assist you and to give you the best drive system that you need. So it's better to consider the possible options. Some are published in the data sheet. And if you consider the options, then you can get what you really need in your application. And our sales engineer are here to give you all the advice and for consultants in order to design the drive system, because we have customization possibility for every part of the drive system to meet your specification in your project. we cannot beat the laws of physics, because maybe sometimes we receive some inquiry, I need a 10mm motor with 150 watts of power. This is not yet possible. We can do the impossible. For the miracle, we still are working on it. Then, starting with the working point. This is a typical diagram that you can see for many motors, and you can see that we have different curve. Now I will explain it. This black one is the speed to torque curve. We start from the no load speed, so without load, you apply the nominal voltage to the motor, and the motor will run at a defined speed. This is the no load speed. Then you see that speed is decreasing linearly down to the stall torque point. Stall torque is where the maximum torque is achievable from the motor. Is also the starting torque of the motor. And you can see that at the stall torque, the speed is 0. You can also see that the motor current is increasing linearly with the torque, and start not from 0, but from the no load current. This is because we have a bearing system, so we have a minimum friction, and this causes a minimum current consumption in the motor. And the third curve is the efficiency curve. You can see that the efficiency curve starts from 0, and you have a maximum peak value around 1/10 of the stall torque. So this is the point where the efficiency is maximum. This is the point where the battery charge reach the longest value. And then you can see that after that, the efficiency go down almost linearly down to 0 on the stalled torque. The efficiency is defined as the ratio between the input power, so the electrical power, and the output power, means the mechanical power. We have some losses because of friction, because of other losses in the motor, but we have the optimization of our products that you can reach very high efficiency. Typically, most of our motor is more than 80%, also 90% in some motors. Then you have the power. The maximum power is reached around half the stall torque, and this value here of maximum power, the efficiency is around 50%. So this is a typical curve. One working point is defined by speed, by a torque, by efficiency, calculated power, and you will see later in the examples. We can divide in 3 parts this diagram. Where the efficiency is maximum, this is the region of continuous operation. This is the region where the lifetime of the motor is longer. This is the region where the lifetime of the charge of the battery is longer. And this is the ideal condition for continuous operation. Fan, pumps, for example, wheeled robot running with a constant speed, belt systems, and so on. When we need a high power, so we go in this region here when the maximum power is achievable, then it's better to go with intermittent operation. This is because the temperature of the motor will rise when the motor is running, and then when the motor is stopping in intermittent operation, the temperature will decrease. So we have a trend up and down, but that trend that is unless we reach a stable value. And we will see one example about this later. The third region is the region of impulsive operation. In this region, the torque is high. You can see the motor current is very high. This causes extreme fast heating in the winding. And this causes increase of the temperature of the winding up to the dangerous value, critical value, and we don't recommend to keep the motor in this condition for a long time. So typically we need a short time, typically for lock mechanism, for example, 1, 2, 3 seconds of on time, and then stop the motor and keep the motor cooling down. If we consider this area here of maximum efficiency, then you can see that we provide our operating diagram, and this is for a DC motor, for example, and you can see we have three main regions. The first one is with a plastic flange. When the motor is connected to a plastic flange, you have a certain area of performance in terms of torque, for example. Here we can reach 25 or 24 millinewton meter. You see this line here is the speed to torque curve, starting from the so-called no-load speed. We have seen it before, and then going down almost linearly. You see here this is bending. Why? Because at a certain temperature, the let's say the resistance of the motor winding is increasing because it's increasing with the temperature. The magnet get a little bit weaker. So this means that this is not exactly like this theoretical curve linear, but is more, let's say, a curve, something like this. And you can see this point here is the nominal point that nominal working point that we are publishing now in our data sheet. This corresponds to the thermal limits of the motor when the speed is, in this case, 5,000 RPM, and the torque is something like 32 millinewton meter. Over this, you can have more performance of the motor, but only in intermittent operation. So you are in the area of maximum power, and you need a little bit of time to let the motor cool down. So a typical application is robotics, when the motor is operating for a certain amount of time, then the motor stops, inversion of the motion, and so on. But you need a little bit of stop time in order to let the motor cooling down. We have some limitation. You see here in this diagram, we have a limitation, a recommended limitation due to the commutation system. If you have a high speed and also high torque, you are in this area here of maximum power. The lifetime of the motor under this condition will be not longer. You can increase the speed, of course, but you can expect a shorter lifetime. So this is to protect the commutation system from worn out in short time. On the other side, we have the winding temperature limitation in this side. And with the winding temperature limitation, we need a better dissipation or an intermittent operation, like you see in this region here. When we talk about a brushless motor, we have a much higher speed. You see the diagram is very similar, and let's say the speed in this case is a 1660 motor. High speed, we can reach almost 100,000 RPM in this case, and you see that this is the nominal curve. When we apply the nominal voltage, the motor with a no speed is something like 52,000 RPM in this case. And when we increase the torque, the speed decreases slightly following this curve here. This is the nominal curve. One characteristic of the motor is that the flatter this curve, the stronger is the motor. So we can compare two different motors, comparing the slope of this line. Also in this case, we have three different regions. This one is with no dissipation, so in isolated motor, let's say for a hand tool, for example. In this case, the motor is with a so-called RTH2 reduced by 50%. We explained the RTH2 and the thermal characteristics in another webinar that we did in the past. Typically, the RTH2 is the thermal resistance between the housing of the motor and the ambient. If you have forced cooling, you can reduce this thermal resistance. This means that the motor can have more performance. And in this case, in this point here, we have typically 25% of dissipation. This means the motor connected to a plastic flange. And in this point here, we can get more performance in terms of torque. We can reach 17 millinewton meter with 50% of reduction. This means that the motor is flange of the motor connected to a metallic flange. Also in this case, we have some limitation. We don't have limitation due to the commutation system, because in brushless motor we use electronic commutation. We have a limitation due to the bearing characteristics. And on the other side, we have a power limitation due to the temperature of the winding. So this limits the performance in this case. Also here we can see the region where we can work in intermittent operation, where the motor can operate at maximum power and then stop for a certain time in order to cool down. The better the thermal dissipation, the better the performance. As you have seen before, we can reduce the RTH2, so that the thermal resistance with a, let's say, a better surface where the motor can dissipate heat, or with forced air in order to get higher performance in terms of torque. So let's maximize the battery charge. When you have a hand tool operated by a battery, for example, the maximum charge lifetime is achieved with high efficient drive system. So you have to select components with highest efficiency. So direct drive operation means using the motor alone without any mechanical gear attached to it. This is the way to have the best overall efficiency. We don't have any mechanical device connected, so the efficiency reach a very high value, and we will see later how to get it. If we have a high dynamics or in the application with fast acceleration, we have a lot of current peaks due to the change of speed. Due to the acceleration, we need torque. We need high current, and this current peak affects the battery charge. In some projects we saw application with supercapacitor, but we have some limitation of the supercapacitor in order to get the maximum voltage. Every supercapacitor has something like 2.7 volt, 3 volt. So if you have a 12 volt, you have to use 4 supercap in series, and then you can have a sort of trade-off in order to get the immediate high current peak and saving the battery. So one advice is to limit, if possible, the acceleration. With our motion controller series, you can use the so-called S-curve. So this means that the acceleration change not in a discontinuous way, but in continuous way, in order to get a better acceleration and to avoid some peaks of vibration during operation. Or better than nothing, if you have a simple drive electronics, you can build up a linear acceleration, so changing linearly the voltage. But if you apply the full voltage, in this case, you will have a lot of peaks of current during startup of motors, and then also the motion is not ideal. When we talk about DC motor, if you operate the DC motor with a DC voltage, so connect directly a battery 12 volt with a DC motor, and then in this case, if you work in the maximum efficiency point, this means 1/10 of the stall torque more or less, you have the longest battery charge lifetime. This is because the motor runs at its maximum efficiency. If you increase the torque, then you can see the efficiency go down and you reach the period of maximum power. This means that the motor must be turned off for a certain amount of time. So you work in intermittent operation. Typically, we have a motor with precious metal commutation. This is the type of technology of motor that reach the highest efficiency. We reach almost 90%. Low current, low starting voltage. This is ideal to use it in battery-operated device. Of course, you may have a necessity to design electronic driver or to use a chip using PWM frequency. So we advise to use a high PWM frequency in order to reduce the losses in the motor. In our motion controller, we reach 100 kilohertz, 92 kilohertz in the speed controllers, and virtually this is double because of the particular PWM scheme that we are using. Remember that when you are using drive electronics, motor, maybe a gearhead or a screw, the total efficiency, the drive system efficiency, is the multiplication of the efficiency of every component. So at the end, you have a value of efficiency, then you have to choose the components in order to get the highest value possible. In our FAULHABER Drive Calculator is able to give you the value of the total efficiency, so it's quite easy to select the high efficiency motor in this case. When we talk about the gearheads, then you have in no load condition, you see this diagram here, in no load condition, and you see that the efficiency is 0. We reach a maximum efficiency around the maximum value at the nominal torque, and you see here that depending on the number of stage, the efficiency is decreasing when we increase the number of stages. This is logic, because when you add a new stage in the gearhead, you add more friction, because you have friction between the gears and between one stage to the other, and so this affects the total efficiency because of increase of friction. The lubricant affects the efficiency. We use a standard lubricant in our standard gearhead system, for example, and you can also have another type of lubricant. For example, when we use extended temperature range, we need another type of lubricant. We have to know the characteristic of your application to use the correct lubricant in order to give you exactly what you need. So this also affects the efficiency. We have to make other tests and to deliver to you a suitable data sheet with the correct data, because everything depends on the components that we are using. Linear actuators are very similar to the gearhead. You can see that also in this case with zero load attached, the efficiency is 0, and then the efficiency is rising and reach the maximum at the nominal force. Ball screw, in this case, you can see that they can reach the highest value of efficiency in comparison with the lead screw with a standard nut. Typically, lead screw may have half of the efficiency. Ball screw can reach 95% of the efficiency, but the lead screw reach low efficiency. This is because lead screw mainly the working principle is that the nut is sliding on the thread of the screw, and the ball screw has a rolling mechanism inside the nut, so you have a lot of sphere, and this causes less friction. This means higher efficiency. So working in the zero load condition is the worst case for a drive system. But if you remember, the motor reach 0 efficiency at the 0 torque, and also here you have 0% efficiency. So working at low load is not the ideal. We have to reach more or less 40% of nominal value related to the torque in order to have a good value of efficiency of the drive system. We also have a gearhead linear actuator. This combines the efficiency of a gearhead and the efficiency of a screw, and we can reach almost 2000 Newton of thrust force in this kind of linear actuators combined with the gearheads. So how to maximize the speed? To go fast, you have to work on the voltage applied to the motor. So the supply voltage affects the motor curve. You can see in this case we have a 1660 a brushless motor like this one. This is for example, if you have a dental application where you need a high speed, or a cutter, for example, you can use this motor. We can reach 100,000 RPM, and to reach higher speed, you need higher voltage on the motor side, because you can see this is the speed to torque curve at the nominal voltage. This means that when we apply 24 volt, we have a starting voltage, starting speed, a no load speed of something like 52,000 RPM. If we need higher speed, so to reach, for example, 70,000 RPM, we need a higher voltage applied to the motor. So we can reach this working point here related to a higher speed. But what happens to the motor temperature? The motor temperature will rise because we will have higher voltage applied, and the motor resistance is the same, so we have a higher current, we can reach a higher stall torque, we can have much better performance in this case, but the temperature of the winding will reach the critical value faster. So we have to take care about this value, and when we simulate the working point, we will see what is the temperature in the winding. Typically, DC motors are not recommended to run at high speed because of the limitation of the commutator. You can go almost double the speed, but don't expect to have a long lifetime of the commutator because at high speed, the worn out of the commutator is faster. So brushless motor are the perfect device for high speed operation. Typically, the speed depends on the number of poles. So 2-pole motors are the fastest one. Then we have the 4-pole motors, more suitable for higher torque and medium speed. And then we have the BXT series, is a multiple pole motor. We have 14 pole, and in this case, the torque will be higher, but the speed will be maximum 10,000 RPM. We can reach 100,000 RPM in 2-pole motors. We reach 10,000 RPM with the 14-pole motors, and we can reach in between around 10,000 or 15,000 RPM with the BX4 with the 4-pole motor, almost 30,000 RPM in certain applications. Anyway, the 2-pole motor are faster if you need speed. When also high torque is required, so in this case, so it's necessary to use gearheads. With the GPT series of gearheads, we can reach high input speed, 10,000 RPM or to 24,000 RPM, and then you have to divide this input speed by the reduction ratio. If you have a 3-to-1, 24,000 RPM, you reach 8,000 RPM on the output shaft speed. Let's take an example using the FAULHABER Drive Calculator. We have a conveyor belt rolling system. 500 RPM is the motor speed, 1 Newton meter is the torque. The size of the rolling system is 42 millimeter in order to integrate the motor inside the rolls. We can see what is the limit of the speed. So let's have a look at what happens on our website. So let's choose this is our FAULHABER Drive System website. If you go here in the middle, you can see the drive calculator. So we can click on the Start Drive Calculator, and then here you see that we open this drive calculator system. So the load speed, we have, say, 500 RPM, if I remember well. Yes, it's 500 RPM. Then 1,000 millinewton meter of torque. We have a limitation on the diameter, so let's put 42 millimeter here. Maybe we can have, let's say, we can keep like this, but maybe 200 millimeter about the length. Mounting type, the photo motor, we can leave it like this. When I click on the calculate button, the system calculates all the possible combination, and you can see here we have a 54 possible solution. So in order to narrow this kind of range of solution, we can use the filters. If you use the filters, for example, the load voltage, if you have 24 volt power supply, you can choose this one. So we reach 20 possible solution. If you want to have a high efficiency, more than 60%, because maybe it's a battery operated, or you need a green device. So you have now 7 solutions with quite high efficiency overall. If you want to have the lowest temperature value, then you can choose between 61 and 85. More than 150 is not recommended because we are on the limit of the motor winding. You can see that we have the 2 possible solutions. This is a DC motor, 38 millimeter diameter, 90 millimeter length. So with the compare solution, we can compare the 2 motor solution. So in this case, you can see that we have 2 possible motors, and what can we use it? Let's have a look. This is near 24 volts. The temperature is 76 on the winding temperature. In this case, the maximum is 155, so we have enough margin. You can see that we are in this part here of the diagram. This means that we need to attach the motor to a metallic flange to reach this easily this working point here. Then you can see here the efficiency is quite similar. If you need to reach a higher speed and you have 24 volt, I don't recommend to use this one because you need higher voltage to reach higher speed. So we can select this one. On the solution details, you open this page here, that you can see the operating diagram. You can see all the calculated values. The calculation engine take care about the temperature variation. So if you change the ambient temperature, you can also change this kind of value. The winding temperature reached 76 degrees, and you see the efficiency overall is 74. And then below you see the characteristic curve. You see by here we are operating in the region of maximum efficiency. So we are in the best condition for the motor. You have suggestion for the drive electronics, an external motion controller, or embedded motion controller with a plug-in. If you have your own your own electronics and you want to plug in the motion controller, you can do it with this new motion controller, or you can use a simple speed controller to operate with this kind of motor, the 5008, 50 volt, 8 ampere of current. If you want to know what is the maximum speed achievable, then you can simply modify the input value and play with the value of speed, for example, to go to 580 RPM. You can calculate with the same condition. The system give you the new value. You can see 78 degrees. So you can go even higher. In this case, you can see that when we increase the speed, we can reach the point of maximum efficiency. Let's modify again to reach, for example, 650, crossing fingers. Then we calculate everything. You see 80 degrees. So we have a good value. You see here the output power is in red, 68. This means that, looking at the curve, the speed is high, the torque has a certain level, so power is torque times speed, and this is the maximum recommended value of 60 watt. And this is the curve. You can see here the black curve is the curve related to the working point, 68 watts. The maximum is 85, so we can also increase, but in this case this note here is a note that the power maximum is exceeded, and this may affect the lifetime in the application. So this can be, let's say, one way to understand what is the limit. You can go high with the speed again, but don't expect to have a very long lifetime. In case of a graphite commutated motor, we can reach exceed 5,000 hours of operation, but if you have a high speed, and like in this case, the lifetime can be reduced. It's very difficult to estimate what is the lifetime of a mechanical system, electromechanical system like this one. So you can see here in this case we reach the maximum efficiency point. Here you have interesting information about the motor drawings, for example, the download section. You can download this document here, the solution details. This is a document where you have all the numbers summarized, what you selected, what is the working point, and etc. And you find the data sheet in 5 different languages. Technical information is another interesting document. The 3D CAD file, if you want to integrate easily this motor in your CAD system, is a zip file. You can download the format you need. The data sheet of the gearhead, technical information related to the components, and so on. So this is the download section. Then your requirements is a summary of what is this application and in contact, we can keep in contact with us. In order to write a message, you have to enter your data, so we can in this case we can see what is we can check together with you your choice. We can advise something new, something better, or alternative for this. If you need a different mechanical range or different shaft or connector and so on, we can collect your information, your requirements, in order to give you what you need. Good. So going back to the website, and then okay, this is a next chapter related to the maximum power. How to reach the maximum power? This is possible, we have seen it before, when you work in intermittent operation. We have to take care about the maximum winding temperature. This must not exceed the critical value. Typically is 125 degrees for most of the motors. For the largest motor, we reach 155 degrees. We can also design specific coil with specific components in order to reach higher temperature, for example. This depends on your requirements. You can see from this diagram here, during on time, the temperature in the winding is rising very fast. During off time, the motor cool down, rise up in the next cycle, cooling down. And this, you see the trend that give you an idea that after a certain amount of cycles, we reach a stable temperature. The blue line is the housing temperature. You can see that the housing temperature rises much, let's say, the speed of increase of temperature is lower. This means that if you place a thermal sensor on the housing, let's say, of your motor, then what happens? That you measuring the housing temperature. You cannot measure the temperature in the on the winding. So this is quite dangerous, because if you reach 100 degrees on the housing, the temperature in the winding can be easily over the critical temperature. When these characteristics last longer, for a long time, then the motor can be damaged. So it's important to set a certain number of cycles and to stay below the critical value of the motor temperature. The drive calculator can assist. We will have a new example later. This is, for example, a high-speed cutter, 15 seconds on, 50,000 RPM to start cutting, and then 5 seconds when the material gets hard, then get harder, 5 seconds at 2,000 RPM and 30 Nm of torque. The cycle needs 20 seconds of stop, and we have 200 cycles in this operation. So let's have a look how to operate with this. We go again, instead of this example, you can find it in the documentation. You can download it probably here or there in your console. You have a PDF file. So let's going back to the FAULHABER drive system. Here you find the drive calculator. For this kind of requirements, we need intermittent operation. So let's choose the operation type intermittent, and then we enter. So the first load speed is 50,000 RPM. The required load torque is 10 millinewton-meter. The time is 15 seconds on. Then we need to add a new line for the other speed, so it's 5 seconds of 2000 RPM at 30 millinewton-meter and 5 seconds, and the time off is 20 seconds. Let's choose a number of cycles of 200, and let's start to calculate everything. If we have on the global settings, maybe we can have some limitation, but let's keep it like that. And for the beginning, we can try to use this value. So when we click on the calculate the system, you see we have 4 possible solutions for these requirements. Motors, since the speed is very high, it's not recommended to use a gearhead, so the motor is in direct connection with the load. And we have several possible solutions. You see here, for example, 120 degree. We don't recommend to use this one. So we can select, for example, these three motors. We can compare up to three solutions in this case. So let's have a look at what happens here. We have we need more than 24 volt to reach this high speed, and you can see that the temperature up and down reach a stable value around 70 degree in this case. In this case, we reach 92 degree in the winding, and more or less the same value also here. So we can choose, for example, this one, 2057, and then you can see the temperature diagram, the up and down value of the temperature for each cycle, and then we reach the final value of 71 degree after more or less 200 cycles. Also, in this case, you have the data, the download, the contact page to get in contact with us for this drive electronics, for example, the SC5008, or this is a plug-in version where you can integrate this in your electronics without housing. Again, if you want to modify the input value, you can go there and change the value. When we operate, this is the next argument related to the high torque. When we operate the motor in high torque operation, we have to take care about the temperature of the winding. And at stall torque, the winding heats up very, very fast. Because we typically have a constant voltage applied. This means that the temperature is rising because of the motor current is rising. We reach the maximum torque. The resistance of the motor is rising, and so the motor torque tends to decrease because of the higher temperature in the winding. So we can reach the maximum torque for a very short time. This is an example. For example, 1 or 2 seconds. This is an example for 2 seconds on. You can see that the motor temperature, the winding temperature, reach value of 53. So if you have 3 seconds, most probably we can exceed the 125 degree. And then you have to operate the motor in one shot, very short time, and then let the motor cool down. Of course, in this typical case, it's difficult to use the drive calculator. So our sales engineer, our R&D, is available in order to advise what is the right motor for selection for this application. If you use a gearhead, you can reach a greater torque. You can also use a smaller motor for the same task. But in this case, we have to take care about the possibility to, let's say, to have if you need a hard stop, for example, in a machine, the motor operates a screw, for example, you go to a certain position, and then you have a mechanical stop. We have to take care about this moment because we have to limit the motor current. Otherwise, we have a shock in the gears, in the gearhead. So don't use the maximum currents in the motor. You need to use the PWM wisely in order to reduce the motor current when you have to operate near the mechanical stop in the system. Under this condition, if we use brushless motor, this is okay. Graphite commutated motor is much better than precious metal commutated motor because of the more robust commutation system, while stepper motor and brushless motor are more suitable for this game. We don't have the limitation of the commutation system. We have a higher cost because of the drive electronics to add in this case. But if you use a motion controller also with the DC motor, because maybe we need an encoder, we need some positioning tasks, then in this case, the investment can be slightly higher. So to reach a long lifetime from a drive system, we need to play with the compromise. We are engineers, we don't like the word compromise, but sometimes in many cases, we have to do a compromise in order to reach what we need. If we want a long lifetime, then we can work at the maximum efficiency point. especially for DC motor, this is the point where the DC motor lifetime will be longer. Brushless motor or linear motor and stepper motor, they don't have problem of commutation system, so they have this system reach the longest lifetime available. And we talk about more than 25,000 hours in the ideal conditions. Planetary gearheads reach a longer lifetime than spur gearhead. We had one webinar in the past related to the planetary gearhead. I just want to show you how to, from our website, you go to the know-how section and then the webinar library. And here you can subscribe, and for 1 year you can follow any of the past webinars that we did. We talk about every motor technology. We talk about application, for example, for space application, for automation, for medical, and so on. And you can find a lot of information about how to use in the best ways possible our drive systems. Pay attention to the axial and to the radial load, especially for the mechanical components, gearheads, but also for the brushless motor and the stepper motor and DC motor because of the limitation of the bearing system. Respect the recommended value because of the temperature of the winding must be contained under the critical value. With DC motor, avoid high current peaks because this affects the lifetime of the commutators. And with gearheads, we don't recommend to have very rapid speed inversion. Use acceleration, like S-curve acceleration, in order to accelerate in a right way all the gears inside the gearhead. Avoid hard stop without limiting the motor current because this may cause shock to the gears, and this may have a problem and reducing the lifetime of the components. So we reached the end of this webinar. To conclude, you have seen we cannot do miracle. It's not possible to have a small drive system with the maximum speed, the maximum torque, the maximum lifetime at the same time. We have to find out a compromise for this. If we work at the maximum speed, so we need to shift to the maximum efficiency region. If we have a maximum power, so we go to intermittent operation and so on. So this is a compromise that you need to deal with when talking about a small drive system. We have seen that the brushless motor have a higher performance because no commutation system limitations, so better performance than DC motors. But we have to respect the thermal limits, for example, the bearing, axial, and radial load, for example, the operational condition. If you are working in a 80-degree temperature, don't expect that a higher performance motor can reach you have a limit, 40-degree limits in this case, to reach the critical temperature, for example. The maximum efficiency give the longer drive system lifetime in operating, especially DC motor with DC voltage. You can get the longest lifetime. Intermittent operation is recommended for maximum power. And you have seen how easy it is to use our drive calculator in order to select easily a drive system, to simulate the behavior in different conditions, change the temperature, change the voltage, change the speed, and you can see with the same drive system what is its behavior. With a filter, you can narrow the selection to a few motor. If you have some, let's say, trouble in the selection, we can assist you in the use of this drive calculator. It's quite easy, and you also have the chat function to that. And last but not least, we are able to design the drive system to fit your application requirements, whether you need extended temperature range, vacuum operation, maximum performance to get the longest lifetime. We can sit together and see what is your requirements in order to give you exactly what you need in your application. You find a lot of information in the FAULHABER webinars page. I've seen it before. Then you have the drive calculator if you want to select the drive system. We have movies in how-to video, for example, in the YouTube. You can find it. We have one section about application notes and tutorial inside our website in the knowledge section in order to give you the best information as possible that you can use in the best way as possible our drive system. So we have reached the end of this webinar. I'm looking forward to see you again at the next one. So see you soon.